So hello everyone, I'm Shen. I will present our paper on Bitcoin Cash target recalculation functions. This is a joint work with Professor Juan Garay and me at Texas A&M University. And in this paper, we choose Bitcoin Cash as a representative of the blockchains that have experienced different target recalculation functions and give an analysis of how these functions affect the security of a blockchain. So for Bitcoin Cash, it is a cryptocurrency and was created on August 2017 from a hard fork of Bitcoin. The motivation for this hard fork is to accommodate an increasing number of the transactions. And this is achieved by enlarging the block size to improve the transaction throughput. So this is a comparison of the, the mining hash power on Bitcoin Cash and Bitcoin. And you can see that actually the mining power invested on Bitcoin Cash is only about 1 to 2% of that invested on Bitcoin. However, the recent data shows that actually the Bitcoin Cash blockchain, it achieves a steady block generating rate when compared with Bitcoin's blockchain. And this means that the new target recalculation function in Bitcoin Cash blockchain, it works well. So before we talk about Bitcoin Cash's target recalculation functions, let's first take a look at Bitcoin's target recalculation mechanism. So it is well known that Bitcoin uses M equals this 2016 blocks, which is approximately 2 weeks to adjust its targets. And the new target is based on the previous target, on the target in the previous epoch, and is adjusted proportional to the time elapsed to generate these blocks. Besides, Bitcoin also has some mechanism to solve this rising difficulty attack by setting the upper bound and the lower bound on how much the target can be adjusted once a time. So let's move to Bitcoin Cash. Since its creation, Bitcoin Cash, it has 3 different target recalculation functions. The first one is this called emergency difficulty adjustment, or EDA. And this is a combination of Bitcoin's original algorithm plus some emergency policy by decreasing the mining difficulty by 20% if the time difference between 6 successive blocks was greater than 12 hours. So apparently this is not a very good solution because 12 hours can be too long for both the miners and the clients. So therefore, in November 2017, Bitcoin Cash adopted a new target recalculation function called SMA for the simple moving average function. And in this SMA function, target will be adjusted after each block. And we have something like a moving window with length of 144 blocks. This is how this SMA function looks like. And you can see that it is quite similar to Bitcoin's function. The difference is that it replaces the target of the previous epoch by this average target. And this is the average target in this sliding window, which has a length of 144 blocks, approximately the number of the blocks produced in 1 day. And here, this M refers to the length of this sliding window. This picture shows how this function works. So first, we have a sliding window, and we move this sliding window 1 block by 1 block to determine the target of the next block from this average target in this sliding window. And recently, it is in November 2020, Bitcoin Cash adopted its latest target recalculation function, which is called absolutely scheduled exponentially rising targets, or this assert function. And in this assert function, targets are still adjusted for every block. However, it has some unique mechanism. So here, first we choose a block as an anchor block and denote its target by T0. And then for all the subsequent blocks, their targets are recalculated based on the target of this anchor block. So you can see here, the next target equals this T0 times 2 to the power of this expression. And here RV refers to the block's timestamp and V is the block height. Also here M is a constant parameter, which we call the smoothing factor. And we will show later in our analysis that actually this is a very important parameter. So for more mathematical facts about this function, we refer to this paper. And this picture shows how this assert function works. You can see that first we pick up an anchor block. Once we pick this anchor block, then we have its target T0, and we have some constant M value. And then for all the subsequent blocks, their targets to say decided by their timestamp, their block height, and this anchor block. So you can see that actually this is something like a memoryless process. That's because now for the current block, its target has no relationship with all the previous blocks except this anchor block. So now we have 3 different target recalculation functions. It is natural to ask which one is the best, or say how these functions affect to say the security of our blockchain. So for our paper is the first formal analysis of Bitcoin Cash's target recalculation functions. And our main framework is the Bitcoin backbone protocol to analyze the security of the Bitcoin Cash protocol. However, in this presentation, I will not go through the details of this backbone protocol, but will focus on how we insert these new target recalculations into this backbone protocol analysis. So here, the crucial part is that we have an intermediate property, which we call goodness in this backbone protocol. And it has a close relationship to those target recalculation functions. And this property is used to show that the block generating rate is steady, or to say close to the ideal block generating rate. So after we replace the original function with this SMA function, our proof for this goodness generally follows the approach in GKL17. But we also improved some proofs to overcome this adoption of the average targets and things like the sliding windows. We also work out some new conditions that this analysis should satisfy. And in addition, we noticed that after using this assert function, all the previous analysis, they collapses. That's because all the previous analysis on goodness, they are based on something like an epoch. However, in this assert function, because it is memoryless and we do not have things like an epoch, so all the previous analysis fails. So in our paper, we use some new analytical tools to prove that this assert function, it actually can achieve the steady block generating rate. So first, let's take a quick look at our model. Our model generally follows that in GKL17 with a delta round bounded network delay. And we also assume the monotonically increasing timestamps, which is slightly different from the real world protocol. And we will carry out our analysis in this respecting environment, which is neither static or permissionless. And the reason is that it is impossible to achieve any desired property in the permissionless property. That's because consistency and liveness can be broken when the number of the parties increases or decreases rapidly. Therefore, our analysis will be in this, which we call dynamic respecting environment. We will bound the fluctuation of the number of the parties in a fixed number of the rounds. And what we want to achieve are 2 blockchain properties. They are common prefix and chain quality, which states that the local view of the honest party can diverge for at most k blocks, and the percentage of the adversarial blocks in the stable part of the blockchain is bounded. And this table is a summary of our parameters. We highlight that the most important parameter is this m, the smoothing factor in the assert function. And we let it be a polylogarithmic function of kappa, where kappa is the length of the hash function output and is also our security parameter. So back to this goodness property in the assert function. So here, once we have the anchor block, we can assume that the value of this T0 and the M, they are constant values. So our observation is that the next target in this assert function is only with respect to the current timestamp and the block height. So which means that once we fix the sequence of the number of the parties, we can compute something which we call a calibrated timestamp, that for this specific block, if it has a timestamp which equal to this calibrated timestamp, then it will have block generating rate exactly f. And one step further, we can also work out this range for the timestamp for this block to have a good target recalculation point. Then what we do next is that we convert our observations into a random variable, which is used to describe the deviation of the calibrated timestamps. And you can see here x1 equals 0, which means that we assume a good start, which means that there's no deviation at the anchor block. Then then we can compute to say the next deviation based on the previous block's deviations. So here we have 3 parts. The first part is the time elapsed to mine this block, and the second part is the ideal block generating interval. And the third part is used to absorb the influence of the party fluctuation. And we can also convert the timestamp range in the previous slide to this condition that this random variable should satisfy. And this means that as long as the random variable satisfies this condition, then this goodness property is never broken. So here we have some problem. That is, we cannot bound the accumulation of the party fluctuation, which is the third term in the previous slide. And this is because in our definition of the respecting environment, we allow, this sequence of the number of the parties, it allows for the exponential growth. And even if we bound the total running time as a polynomial in our security parameter, it is still not enough to remove this term in those steps. So what we do is that in our analysis, we still need something like a sliding window. So in this sliding window, we will associate all the blocks timestamps with the timestamp of the first block. And recall that in the calibrated timestamp, we associate all the timestamps with the timestamp of the anchor block. So here we associate the timestamp with the first block in this sliding window, which we call it the relatively calibrated timestamp. And because we can bound the party fluctuation in this sliding window, so we can have some ways to remove the third term in the previous slide. So here we will define a new random variable wi, which is to describe the deviation of this specific calibrated time, which we call the relatively calibrated timestamp. And we can also convert the conditions that a random variable should satisfy to this new condition. So remember that we have a sliding window. And after we have all these preparatory works, what we will do is that we will apply a state-based analysis, which means that we will divide this range, or the condition for this random variable into five different states. You can see that here are the dark green state, light green state, and blue state. And we also define some red states to indicate that some bad events happens, which means that if our random variables, they reach these bad states, then it means that the goodness property is broken. So what we want to prove are two things. First is that we want to prove that within a sliding window, this goodness is never broken, or never violated. And we can move this sliding window from the beginning to the whole execution. So here first we have a sliding window with some blocks BU to BV. And so what we want to prove first is that if our random variable, it starts in these three states, in this light green and the blue states, then the probability of it once reach this bad state is negligible. So this shows that in this sliding window, the goodness property is never broken. And what we want to do next is we want to move this sliding window from the beginning to the whole execution. But it is slightly different from the intuitive solution, like to move it one block by one block. So how we move it is by the following steps. So first, we want to prove that if our random variable starts within these three states, then in this sliding window, we can find a block which is in this blue state with overwhelming probability, which means that it is always feasible to find such a block. Then we can construct a new sliding window based on this new block, which is in state code. And since we construct a new block, we have to associate the relatively calibrated timestamps to this new block. So we will have some state conversions. But we can prove that this state conversion, it will always convert to these safe states, which is the safe state in this point 1. So combine this point 2 and point 3, then we get an approach to move this sliding window, which is to, you can see that we can move it from the beginning of the execution and find an appropriate block and then move this sliding window. And this happens with overwhelming probability, which means that we can always do this so that we can extend that this goodness is never violated from the beginning to the whole execution. So this is our analysis for this assert function. And after we insert our analysis of the assert function into the backbone protocol, we can work out some conditions that our analysis should satisfy. And for the last part of our paper, we provide a comparison of our analysis with the real-world network. So here we need to extract some real-world network parameters like the party fluctuation ratio and the network delay. So for this party fluctuation ratio, what we adopt is the daily average hash rate instead of this real-time hash rate. And that's because this real-time hash rate, it fluctuates widely, which is bad for our analysis. And we also have some literature like this temporarily dishonest majority to support our choice of this daily average hash rate. And then we will consider two types of environments. First is the quiet environments, which means that the fluctuation is not widely. And the second one is the environment with wide party fluctuation rate. And the next parameter is the network delay. And we extract it from the block propagation time. And actually, as the network develops, it is now not a big issue in the blockchain protocol. So after we extract all the real-world network parameters, we will parameterize our analysis with these things and check if they satisfy these conditions. So here, these are our conclusions. The first and the second point is for the assert function. We can prove that even under the current parameters, which means that the smoothing factor m equals 288, this functions helps to maintain a steady block generating rate. You can see that the probability that these bad events happen are quite tiny, which means that it can always help to achieve the steady block generating rate. And our most important conclusion is that this assert function is better than the SMA function. That's because we can insert wild party fluctuation ratio into this assert function. For example, if we take this ratio, gamma equals 1.88, then it can still satisfy the assert function, but it will fail in our SMA analysis. And as you may know, there are a lot of other target recalculation functions. So now we are working on a general framework to analyze this mechanism. And that's all for our paper. Thank you for listening.
Thank you very much for your talk, Yu. We do have a couple minutes for questions, so the audience can use the Q&A button at the bottom of their screen to type in their questions for you. And let me start with one question, and just to take a step back from all the complex math here, and maybe give some intuition about what problems can be caused if the m parameter is small. So my question is, what if m takes a value of 1 or 2 in assert? What would a concrete attack look like? How would the execution look like in this case? Would it look similar to a backhack attack, or is it something different for assert specifically?
Yeah, if you choose an m value that is a small number, right? So it will adjust the difficulty only based on some small range of the blockchains. So which means that it can be sensitive to the temporary wide fluctuation. So it can have some very bad influence on the steady block generating rate. So what we prefer is a relatively high smoothing factor. Yeah, but if we
can an attacker take advantage of a small m, and how would they do that?
No. It is a constant parameter in the protocol. So all the parties will take the same m value.
Right, and what if this parameter is set to be a small value? Then can an adversary mount some sort of attack?
I think the adversary cannot change this value because it is something hard coded into the protocol. And it is just like the parameter for this function. So the adversary cannot change it, but they can only mine under this function to determine their targets.
Thank you very much, Yu, for the talk and for answering the questions. If there's further questions for any of the 4 speakers throughout the session, please use the Q&A functionality to ask questions. I'm sure they will be very happy to answer offline.